we've seen that type variables allow us to do generic programming in Java. So we can bring in what's called polymorphism over structures, so structural polymorphism using these type variables. So now let's see how this generics interact with other features in Java such as subtyping. So let's first go back to arrays. So for arrays, if a type S is compatible with T, in other words, if S extends T, S is a subtype of T, then an array of S is also compatible with an array of T. So for instance, if we have our usual thing where we have ticket as a superclass, right, and we have below that we have e-ticket as a subclass, right, so we have ticket and e-ticket. Then we first define an e-ticket array, right, this is a more specific type. Then because it is more specific, we can take a ticket array and assign it an array of type e-ticket. So wherever we see a ticket, remember the logic is that wherever we expect a super type variable, we can associate a subtype value. So with a super type array, an array of type ticket, I am allowed to associate an array of type e-ticket because this is the general type compatibility between super types and subtypes for individual objects, and it extends to arrays. So this is fine. Now let's see what happens if we directly try to manipulate. So notice that after this, ticket array and elec array are both pointing to exactly the same object, which is actually an object of e-tickets, and in fact it was created as an object of e-tickets. But because I don't have this information statically, I could write in my program an assignment to the ticket array directly and try to rewrite position 5 in the ticket array by a new ticket. Okay. But remember that position 5 in ticket array is actually position 5 in this e-ticket array. So it's expecting only e-tickets there because that's how this array was declared. Ticket array was just a kind of alias for this. But at compile time, Java has no way of checking that at this point ticket array, which is declared to be an array of type ticket, cannot take a value of type ticket in one of its positions. So the compiler will let this pass, and of course at runtime, when we find that this ticket array is actually an alias for an e-ticket array, you will get a type error. So this is the kind of situation that we really want to avoid, which is to get type errors at runtime. And unfortunately, because Java arrays have this compatibility, which is called covariance technically in the programming language theory literature. So it says that if S extends T, then an array of S extends an array of T. So this simple-minded covariance is what a programmer would expect. You would expect that I could take something which is a subtype and substitute it in any context, right? So the whole idea is that in a context, right, can I substitute a subtype or not? And it would make sense that in an array context, you can take a subtype and substitute it. But unfortunately, we have this consequence that we get runtime type errors. So in order to avoid this, generic classes, when they were introduced, remember the generic classes were introduced into Java after the language was defined. So by this time, people had already noticed and observed this covariance problem with arrays. So when generic types were introduced, the conscious decision was taken not to have this type compatibility. So if we had type compatibility, then if you substitute T with object, which is of course the root of our type hierarchy, then it should be a super type of a linked list, in this case, with any other type in our hierarchy. Right? This would certainly be true if I had an array of object. It would allow me to substitute it by an array of strings in a concrete situation. But in the generic case, this is not true. So a linked list of a subtype is not compatible with the linked list of a supertype. So in particular, right at the beginning, we wrote this generic find, which took two inputs, an array of object and a value of type object, and tried to check whether that value occurred in the array or not. So if we wanted to print out a list which is defined using this parameterized linked list type, we cannot use object as the super type to make this a generic function, right? So we cannot write a function like this because linked list of string or linked list of manager or linked list of date will not be allowed to be substituted for this. The only argument that I can pass to this function is actually of type linked list object, right? So the way to get around this, of course, is to write generic functions, which we have already seen. So what we can do is we can make the method generic by introducing a type variable. So we can introduce a type variable here before the return type. And what this says is that this function is now parameterized by the type, and this type variable is now being used over here. Right? So this is a generic function, as we saw in the previous module on generics. And this is precisely saying that this angle bracket t is what we call in logic a quantifier. It says for every type t this function works. Right? So for every type capital T, this is a function which will print a list whose underlying objects are of type t. So this is, of course, one standard way of doing it, which we have already seen. But notice that after we pass in the t, we are not using t anywhere inside the function, and we are also not returning any value which depends on t. So we have a free choice of type to enter the function, and once we enter the function, what we are really using is the other part of the Java hierarchy, which says that an object of type an O of type object can be used to hold any value. So we are really taking this get next function in our iterator. So what is this doing? It's using an iterator, right? It's getting an iterator for this list and it's running through the list and is printing out each object in the list. But to store the object before we print it, we are using this fact that in the Java type hierarchy, capital O object is sitting at the root of the hierarchy, so it can stand for any value. And at this point, we are not going to manipulate it, we are not going to call any function on it, we just want to print it. Right? So we just pass it to the print function and it gets printed. So in this case, we are not using this t anywhere. So this is a very special kind of function where the type quantifier allows us to instantiate any type in the argument. But once we instantiate it, we don't need to remember what type it is. There is no dependence of that t anywhere else inside the function, either inside internal variables or in the return type. So when such a situation happens, then the name t is actually not important, right? So we don't really need to remember that it was of type t because t is not being used. So Java has another mechanism to deal with this called a wildcard type. Right? So here what we can do is we can do away with this. Notice that there is no type quantifier here, and instead of t we use this special symbol question mark. Right? So this is an alternative way of writing an arbitrary type. Now of course when I write question mark, it doesn't have a name, so I could not use any values of type question mark. I cannot return something of type question mark because there is no way to compare. But if this is a kind of situation where I am not going to make use of that value anywhere inside the function, then a question mark is fine. So a question mark stands for an arbitrary unknown type. So it's not very different from saying that you quantifier over any. Earlier we said that this said for all t do something. So this is really saying that t is an arbitrary unknown type, but we remember t. So the t that goes in is the t that is used somewhere else, is the t that is returned. So that there is a kind of a consistency with the usage of t. But in situations where that type is not being used anywhere, we don't need to give it a name. And what we save on is this angle bracket notation. We don't have to write anything here to specify that it is a quantified type, right? We just implicitly do it by using this question mark. So this question mark or this generic wildcard allows us to avoid an unnecessary type variable whenever the type variable is not needed elsewhere in the function. So this is just a small shortcut, but it saves you having to write a type variable if you are feeling uncomfortable about writing that. It doesn't, so the two are completely equivalent, right? You can just write the quantifier, you can write angle bracket t and use t throughout the function, or if you don't need t anywhere in the function, in that special case, you can use this question mark. So it turns out that you can actually define variables of this type. So you can actually say that L is a linked list of some arbitrary but unknown type. But for obvious reasons, it's not really possible to add anything concrete to this. So if I take a linked list of this type, right, and then I say that it is at runtime a list of string, the problem is that we don't have any way of knowing what the type is. So the compiler will not allow you to add other objects to this because it doesn't know whether this is compatible or not, because you said it's a list of any type, so it really does not have a concrete type associated with it at compile time, right? So this is the problem. So compiler cannot guarantee that types match. So the moral of the story is that you can use wildcard types quite easily as arguments to functions where the type information of the arbitrary type is not required anywhere in the function, but do not use it in general in order to generate variables and assign values to them. So we don't have to have free generic type wildcard types. So we can have what are called bounded wildcards. So we saw this in the context of type variables. We said we could write something like S extends T, right? So we could compare one variable to another variable and constrain it. So S and T are two different types, but they are related by the fact that S must be a subtype of T. So now suppose we have a super type shape which has three subtypes: circle, square and rectangle. And let's imagine that the super type shape has a method defined to draw a shape. And it so happens that each of these subtypes, circle, square and rectangle, actually override the draw. So if you ask a circle to draw itself, it will use a more specialized method, similarly with a square, similarly with a rectangle. So now the typical kind of thing that we would like to do is process an array which has multiple types of shapes, right? And print all of them using this, or draw all of them, right? So how do we describe a list which can hold any type which is compatible with shape? So we don't want it to be a linked list of anything, but we want it to be a linked list of something which is compatible with shape. Now in the same way that earlier we were just printing out an object, right, when we said the print list command, in this we have a draw all command, and all it does is it takes an object and it draws it. So we can use a simple variable of type object in order to run through this list. So all we need to specify is the list itself is well typed so that draw comes. So this is where now we can use this generic wildcard, but we can bound it by saying that it can't be any old type, it must be a type which extends shape. So we don't care what it is, we don't need to know its name because we are not going to use that type anywhere inside, but at the same time we have constrained it so that it extends shape. So it's the same way that we can take two concrete type variables and constrain one to be a subtype of another. We can take this wildcard and constrain it to be a subtype of some other type. Now we can also use this in the context of type variables. So that was an example where we constrained it with respect to a concrete type shape. But remember our array copy where we took two arrays, source and target, and we said that we can copy a source array to a target array so long as the target is a super type of the source. So we can do a similar thing, for example, with our generic linked list. So we would like to do a list copy which will take a source list and a target list. And now what do we want? Well, we want that this list, okay, is a subtype of this list, right? So the target list must be a super type of the source list, or the source list must be a subtype of the target list. So in the signature of this function, we add this constraint which said that the second argument has some arbitrary type t and the first one has some unknown type question mark, but this question mark extends t. So this is just, I could have equally well written here s and written s here, but it's just to show that you can use this question mark also in conjunction with type variables. So you can use type variables, you can use a question mark, you can use both. And again here the point is that in this array copy, right, we are going to run this iterator through this list and we are just going to pull out the object from one list and we are going to add it to the other list. So we are not doing anything else with O. So we don't need any specific properties of O. So we don't really care what that question mark stands for. Now we can, interestingly, we can reverse this constraint. So instead of saying that the first type is a subtype of the second type, which is what this constraint is saying, we can also say that the second type is a super type of the first type. So we can now say that the first list, the source list has type t, right? And now the target list is any type which is above t, right? So just like extends, you can use super as a constraint. So this is a new thing which we have not seen before, but this is just to show that it's symmetric. So in this example, it doesn't really matter which way you do it, but in case you need to use t for one of the two sides, right, you can decide which side you want to use t, and for the other side you can use question mark. Remember that we need to use t in case t appears somewhere in our code. Now supposing it is natural for the first argument to appear in our code, then we would like to give a name to the first argument and maybe the second argument does not need to be named. On the other hand, it could be that the second argument needs to be named, in which case the first argument may not need to be named. Of course, if both need to be named, then you would use two type variables, which is perfectly fine. But you can have this kind of flexibility to decide which of the type variables can become a wildcard in case you have this constraint between two of them. So to summarize, what we have seen is that Java arrays are covariant, right? If S is a subtype of T, then an array of S is a subtype of an array of T, and this potentially leads to runtime type errors, because we can have a situation where we accidentally try to assign a variable of a subtype to an array which is declared of a supertype through this aliasing that we saw with e-tickets and tickets. So in order to get around this, the generic types are not covariant. So if we have a parameterized data structure, we cannot say that substituting the parameter with object creates the most general type of that parameterized type. So a linked list of object is not a supertype of a linked list of string, even though object individually is a supertype of string. So instead we saw that we can use type quantification in order to make things generic, but we've also now seen that there is a special situation where we can use this wildcard question mark in place of an explicit type variable. So wildcard in general can be used wherever the type T is not needed explicitly in the rest of the function. It's only needed to specify a kind of constrained or unconstrained access to the argument, but it's not used in the return value and it's not used in any local variables. Then we don't really need to remember what T is when we enter the function. So we can then freely use the question mark to indicate this freedom of choice of type and proceed. And like normal type variables, we can bound our wildcards using either extends or super. So we can describe the fact that we want an arbitrary type which is a subtype of a given type, or an arbitrary type which is a super type. And in all these things, when we say extends and super, these are what are called transitive. It is not saying that these are immediately subtype. It's not that extends, when we write extends in the class definition, it is one step, right? When we say that circle extends shape, it means shape is one level above circle in the hierarchy. But supposing we had ellipse extends shape and then circle extends ellipse, right? So supposing we had a shape and then we have an ellipse, and then we might have a circle as a special kind of an ellipse. Remember, an ellipse is something which has a major axis and a minor axis. So a circle can be thought of as an ellipse where the major and minor axis is the same. So in this case, technically speaking, when you write circle, we would say circle extends ellipse and ellipse extends shape. But in this kind of a type expression, circle extends shape is true. So it is a transitive requirement. Similarly, shape is a superclass of circle, is true in this transitive requirement.